All right, it is Tuesday. You all just left. And that multiple load problem is really pissing me off. So I went ahead and just walked away from that megapascal problem just to verify that our system is good. How I'm showing you is good, and it is. So I want to show you how I do it, just like we were doing it in class. I don't know really what is wrong with that megapascal problem, but there's an example problem on 221 that is the same problem. It's just in the US system. So I went ahead and said, okay, I'm going to work this. Just going to work it for one direction, kind of like we were doing in class, and see if the numbers work out with the example problem. So I'm going to walk you through it. Hopefully you watch and understand, and then I can do it again in class. Because it's not that difficult, but you do have to keep track of what's happening in what direction. So what I tried to figure out here was the dimensional change of the 12 inches. This one, right? So this 98,000 pound load is going to stretch this thing. So the 12 is going to get bigger. This 288,000 pound is going to squish this dimension. 3 gets smaller, but the 12 gets bigger, right? Because it's going to squish it out like a pancake. So I can do this one very easy with just PL over AE to get that dimensional change. But then to get the dimensional change of this 12 inches from this, I have to do Poisson's ratio and deal with the transverse. So I did the first part, and I noted that I'm thinking about the 12 inches or the y-axis as they've defined it. So I have both notations here, and then I'm noting the increase. So the equation I use for that change is PL over AE, P being the load, 90,000, L being the stretch length of 12 inches. Then the area is this cross-sectional area, or 3 times 1, that's this. And then E is modulus elasticity for our mild steel, 30 million, right? Gave me 0.012 increase, stretching from the 90,000. So that one's pretty easy. And that's going to be the bulk of the stretch. Like there'll be a little squish from this, but not much. So this, you don't expect to change a whole lot. It will change some. But to get the change of the 12 from this, you have to first do the axial, just like you did here, but you're doing the change in the 3 inches, right? That's the axial for this one. So I did that. I did 288 and 3 inches. That's the original length here. And then the area is 1 by 12. That's this big area, 1 by 12, this area, right? And then again, 30 million, and I get 0.0024, right? So that's the axial change, 0.0024. Now, you take that and you need to get the transverse, this 12 inch, right? So to set that up, I do Poisson's ratio is equal to the change in the transverse. That's what you want to know. And then the original in the transverse. So the one that I'm thinking about, the one I want to know is this 12 inch. So that's why this goes in. So this is transverse, this is axial. So there's my 0.0024 going in, and the original length of this 3 inches, the axial for the 288. All right. So once that's done, then you just take this number, this is a number, and multiply it into that. And then that becomes equal to this. So the 12 gets multiplied over. And when you do all that, I actually got a change in the transverse of 0.0024. Not fantastic that it's exactly the same as the axial. That's just coincidental. But yeah, doing that times that, and then 12 times that gave me a change in the transverse of 0.0024. That is when you compress the 3, you're squishing out the 12. So that's an increase. So that is also an increase on the 12 inches of that. So you take this now and you add it to this to get the 2 increases, and it came out to 0.0144. 0.0144 for this Y dimensional change, right? Y dimensional change. Total. How does it compare to their number? All the way down here at the bottom is their number. .0144 increase. Exact same number. So how they're doing it and how we are doing it is exactly the same. They're just using the stresses instead of this PL over AE to get this axial change. So this is derived from stress over strain, which is what they're using, right? So it's the same combination, stress over strain, and this same combination, right? If you take this and turn it into P over A, and you take this and turn it into change over L, and then massage all this, you'll get the same equations. So yeah, it did work. Same exact number, 0.0144, 0.0144 increase. So we're good on our process. I just need to figure out like what we're doing differently on the megapascals thing and the metric system. So we get the same answer as the book. But this is a great problem to look through. It's on page 221. It's an example problem, just working it through. So there you go. Now that's kind of off of my brain. I can move on. So we'll talk about it more in class on Thursday, but I wanted to make this real quick so you kind of see the process. Also, failed to tell you in class, but I put on the calendar exam 1, which I have is next Tuesday. So I like to give you a week notice. So when I send the email that says, hey, I made this, this is just a reminder, we're going to go for it next Tuesday. I'd like you to have 2 hours. So if you can build 2 hours into your life, we'll go 1 to 3. If you can't, I need to know that. So, and we'll do something different, but 1 hour is not going to do it on the exam. And I'll talk about that on Thursday, what will be on it. So, all right. Thanks for your patience today. See you all Thursday.